Hello and good day. Welcome to the third and final part of the video lecture on line integrals of scalar fields. The first and second part dealt with line integrals with respect to the arc length s and with respect to the coordinate variables x and y respectively. If you have not seen those videos, I recommend that you see them first. For this part, we will again talk about line integrals with respect to arc length and with respect to the coordinate variables, but this time of curves in three-dimensional space. Let's start. Now we take f to be a function of three variables, x, y, and z, which is continuous on some three-dimensional region which contains a smooth curve c, and where c is described by the vector function r of t, this time with three components, x of t, y of t, z of t, with the parameter t in the closed interval ab. We define the line integral of f along c with respect to the arc length s as the limit of the summation. This time we have f of xi star, yi star, zi star multiplied by delta si, where delta si is still the length of the ith sub-arc of c, where the summation runs from 1 to n, and we take the limit as n approaches infinity, provided that this limit exists. The notation remains the same, except for an f of xy, we now have f of xyz. In addition, we can still evaluate this line integral as a definite integral with respect to the parameter t. What we have is the integral from a to b of, we express x, y, and z in terms of t. So I have f of x of t, y of t, z of t, and your ds is still the magnitude of r prime of t dt. We also have the line integral of f along c with respect to x. It is given by the limit of the summation of f of xi star, yi star, zi star multiplied by, just like before, delta xi, where the sum runs from 1 to n and the limit is taken as n approaches infinity, provided that the limit exists. The notation is the same as before, where instead of f of xy, we have f of xyz. In addition, we can still write this line integral as a definite integral with respect to t. We have the integral from a to b of f of x of t, y of t, z of t, multiplied by dx, which is just x prime of t dt. The line integral of f along c with respect to y is similarly defined. In the limit definition, we have delta yi instead of delta xi, and in the definite integral with respect to t, we have dy to be y prime of t dt. This time, we also have the line integral of f along c with respect to the third variable z. In the notation, we have dz. In the limit definition, we have delta zi, and in the definite integral with respect to t, we have dz to be z prime of t dt. As a remark, the sum of the line integrals p of xyz dx, q of xyz dy, and r of xyz dz, all line integrals being along the same curve c, by convention, just like before, is simply written as the integral of p of xyz dx plus q of xyz dy plus r of xyz dz along the curve c. As an example, suppose you're being asked to evaluate the line integral of x squared sine z ds along the curve c, where c is parameterized by the vector-valued equation r of t, whose components are cosine t, sine t, and t, with t in the closed interval 0 to pi. Remember that to evaluate this line integral, you need to write it as a definite integral with respect to the parameter t. Hence, we have the integral of, we need to write x squared sine z in terms of t. Since x is cosine t and z is t, we obtain cosine of t, quantity squared, multiplied by sine of t. Now, ds, if you recall, is just the magnitude of r prime of t dt. And because t is in the closed interval 0 pi, then the limits of your integration should be 0 and pi. For the magnitude of r prime of t, we need to compute first for r prime of t. Here, r prime of t has components negative sine of t, cosine of t, and 1, which are the derivatives of cosine t, sine t, and t, respectively. Continuing, we obtain the integral from 0 to pi of cosine squared t sine t. Computing now for the magnitude of r prime of t, we obtain the square root of the square of negative sine t, which is sine squared of t, plus the square of cosine t, which is cosine squared of t, and the square of 1, which is 1 dt. Note that sine squared t plus cosine squared t is just 1. And hence, the magnitude of r prime of t here is actually just constant, equal to square root of 2, which we can now factor out of your definite integral. And so we get square root of 2. And now, we can let u here to be cosine t, with du equals negative sine t dt. So we factor out a negative 1. And the integral of u squared is u cubed over 3. So I get cosine cubed t all over 3, evaluated from t equals 0 to t equals pi. The constants simplify to negative square root of 2 all over 3, and evaluating at t equals pi, cosine cube of pi is negative 1, while cosine 0 is 1. So all in all, what I get here is the value 2 square root of 2 all over 3. And this is now the value of your line integral. For the next example, you are being asked to compute for the value of I, which is the line integral of y minus x dx plus z dy plus x minus y dz along the curve C, where C is the line segment from point P to point Q. Take note that in this example, no parametrization for C is given. Nevertheless, since C is just a line segment, all we need for a parametrization for C is the initial point P and the vector from point P to point Q. Here, your vector PQ has x component 2 minus 3 or negative 1. Similarly, has y component negative 3 minus 0 or negative 3, and has z component 1 minus negative 1 or 2. This yields the following parametrization for C. We have the vector valued equation R of t, which has x component, the x coordinate of the initial point P, which is 3, plus the x component of the vector PQ negative 1 times t, or simply 3 minus t. Similarly, for the y component, we have 0 plus negative 3t or negative 3t, and for the z component, we have negative 1 plus 2 times t or negative 1 plus 2t, where the parameter t is in the closed interval 0 to 1. You can verify that at t equals 0, we get the point 3, 0, minus 1, which is point P, and at t equals 1, we get the point 2, negative 3, 1, which is point Q. Furthermore, take note that for curve C, we have x to be 3 minus t, your y to be negative 3t, and your z to be negative 1 plus 2t. We are now ready to compute for the value of I. Remember that our goal is to write this line integral as a definite integral with respect to the parameter t. Hence, we have the integral of, we need to write y minus x in terms of t, and recall that your x, y, and z are as follows. So we obtain y, negative 3t, minus x, 3 minus t, multiplied by dx. Since x is 3 minus t, then dx is negative 1, the derivative of 3 minus t, multiplied by dt. Here we only write negative 1, and we will write dt at the end of the integral. Plus z, but your z is negative 1 plus 2t. And for dy, since y is negative 3t, dy is negative 3 multiplied by dt. Again, we only write negative 3 here, and I will write dt at the end of the integral. Finally, we have plus x minus y, where x is 3 minus t, minus y, that's minus negative 3t, everything multiplied by dz, where z is negative 1 plus 2t. So I obtain dz to be 2 dt. So I write here 2, and I multiply everything by dt. Since the value of the parameter t lies in the closed interval 0, 1, then the limits of integration should be 0 and 1. Now, all that remains is to evaluate this definite integral. First, we simplify by distributing the constants negative 1, negative 3, and 2. We obtain 3t plus 3 minus t plus 3 minus 6t plus 6 minus 2t and plus 60 dt. Observe that negative 60 and 60 cancel, and negative 2t, negative t cancel with 3t. And we are left with simply the integral from 0 to 1 of, that's 3 plus 3 plus 6, which is 12 dt, which is just equal to 12. And that is now the value of I. We are now at the end of the lecture videos on line integrals of scalar fields. I highly encourage you to answer the following exercises. In part 1, you are being asked to evaluate the following line integrals. Parts 2 and 3 involve problems on applications of line integrals with respect to arc length. If you have any questions, comments, or suggestions on these videos, kindly comment them below. Also, please do not forget to view the discussion videos on this topic. That's it. Thank you for your attention, and goodbye.